Advait Gupta, a Stanford University alumnus and the CEO of Paanduv Applications, along with being the lead developer of AM Prava. He will discuss the challenges encountered in the AM industry, but crucially, he will outline Pandav's strategy to address these challenges through the launch of its product, AM Prava. So I invite him to introduce AM Prava and share his screen.
Thank you, Krish. Is my screen visible?
Yes, your screen is visible.
All right. So first of all, thank you, Professor Chakrabarti and Priyanka, for all the academic research insights and commercial insights about additive manufacturing. So we started with a lot of equations in the first presentation, but by the time my turn came, I assure you there won't be any equations at all. And all you will see is a lot of visuals, hands-on demonstration of the product, and basically all the challenges that Professor Chakrabarti talked about in academia, all the challenges that Priyanka talked about in industry. I hope all that will, all those challenges will be overcome by the launch of this software, AM Prava. It's a very straightforward, presentation. Basically, three parts. The macro scale module, the microstructure module, and the AI module, and all these three modules will be demonstrated through the demo, except for a few slides on the introduction. Okay. So the relevance of AM Prava, I think both our previous speakers have done a great job explaining this, why we need a simulation software for developing new alloys, reducing defects, and optimizing process parameters. The thing that we want to add here, what is different between AM Prava version 1.5 and our earlier versions. By the way, we launched AM Prava almost a year ago, and since then we have come a long way in making the software more accurate, more robust, and more user-friendly. When we talk about accuracy, we have added vaporization. So now we are in the four-phase system. We have the solid phase, liquid phase, the shielding gas or the inert phase, and then the fourth phase, which is a metal vapor. That is added to the system. Fresnel reflections, which is the optical or property of not just the material, but also depends on the type of laser you're using. So Fresnel reflections are activated. Marangoni convection, which is temperature dependent surface tension, is activated, and grain evolution is done in a much more accurate manner. It's more robust because it's better tested. On the AI front, our neural networks are more regularized. So those of you who are into machine learning or AI will correlate with this better. You can provide very complex scan patterns, numerical stability, convergence is much better, and your data is backed up in a more efficient manner. So that means even if something goes wrong with the software while it's running, your data is still safe. It's more user friendly for those of you who picked up the snippets of a software. We have no idea how that got out, but now it's a very dark theme, keeping up with the times. We already spent a lot of time on the screen, so we have made the interface quite dark. The visualization is fantastic. It's really postmodern visualization, responsive progress console, and we have a dedicated online user manual as well. So let's start with the macro scale module, and there'll be a lot of visual stuff for your eyes throughout the presentation. So this is the macro scale modeling that we are talking about. At the core of it lies the multi-phase solvers, the phase change solvers, and we are using something. We are working with four-phase systems. Currently, we are providing our software is released for laser welding and laser powder bed fusion. But the type of physics that it's capturing is phase change, particle dynamics, heat and mass transfer, laser dynamics, temperature dependent surface tension or Marangoni convection, spattering, keyhole effects, and pore formation. Okay. Macro scale modeling, again, I won't spend a lot of time here. This is very important. It depends, unstable melt pool is the source of all the troubles in your build part down the line. So we don't want an unstable melt pool. We want a good finished melt pool without any pores. Okay, some of the defects by the way, every single image and media that you will see throughout the presentation is originated from AM Prava. So we start with this lack of fusion where hatch spacing is too high, and the two tracks have not kind of fused enough. Then we have this big porosity defect. We have air entrained in the system, vapor trapped in the system, and these all end up causing a very sort of weak material at the end of the bit. Poor surface finish. Your powder is only half melted on the sides. Keyhole induced porosity. Your keyhole collapses onto itself, and some of the air and vapor is entrapped at the bottom of the keyhole, which is bad. And then you have a spattering, in cases where all of a sudden your laser is turning its direction or laser is turned off. Your melt pool becomes quite unstable, quite dynamic, and then a droplet or two is launched into the system. So that's again a bad thing. Now moving on to the microstructure module, this is stochastic modeling using Monte Carlo algorithms. Again, we are doing this for laser welding and LPBF, and the physics. Again, we are capturing sort of similar but different type of physics at the same time, because heat transfer with conduction is captured. Rosenthal based power distribution, grain evolution, grain misorientation angles, Euler angles, and whatnot. So if you see this video, this is done for Ti 64 material, a sort of a reference material for a laser power of 280 watts and a certain speed. And you can see 3 tracks that are built parallel to each other in a zigzag manner. And you can see how the grain structures have evolved down the line. Again, this microstructure modeling is something that correlates most closely to the real mechanical properties of a built part. When we talk about fracture toughness, crack initiation and propagation, fatigue life, and estimation of any other mechanical properties, this little visual representation that you see on the screen in yellow, this grain in itself can provide a lot of information about these very important mechanical properties. So some of the defects that we can capture using microstructure modeling. So if you observe the grain structure, there are primarily divided into two types of grain structures on this screen: columnar grains, which are kind of long, columnar in shape, and then we have equiax grains, which are sort of circular, not exactly circular, but it's small and spread in all the directions equally. So the equiax grains are desirable because they have less probability of crack propagation, they have high fatigue toughness. However, they may lead to higher corrosion probability as well. And large columnar grains are not desirable because that give you high probability of crack propagation. So these are very critical aspects of building a part. Final module, which is the AI module, is purely neural networks based, deep neural networks for predictive modeling. It is agnostic to the type of data you throw at it. It is agnostic to the type or the complexity of physics you throw at it. It can work on extremely nonlinear and coupled additive manufacturing physics, which is typically the case, and it is able to predict, really based on how complex you desire to choose your model. This is in the hands of the user. You are really free to choose that. So. Let me explain the importance of AI in additive manufacturing. So we saw that we are already aware that in our previous talks that experimental data takes its own time and consumes certain amount of resources. You want to try a new set of process parameter and alloy properties. If you take it to an experimental route, you will probably end up spending months of your time, if not a year. And then at the end of the process, you will probably discover a new alloy. You will probably reduce defects and optimize your process. If you do the same process using computational physics, which is a big aspect of our software, this 6 months of time can be reduced down to a few days maybe. But still, it's almost a crime not to use the data that you already have from before, whether it is experimental or computational. So what this module does, you input your new process parameter and alloy properties into AM PravaH's AI module, and based on what the model has already been trained upon from your previous data, it can, within a matter of 1 second, it can predict your alloy defects, and process optimization can be done as well. For example, this is a new set of alloy properties. nobody knows if we put in these, if you use these sort of alloy properties, what will be the weld width. Nobody knows that. But let's say I have a trained model which has established some sort of non-linear non-linear connection between this input parameters and output parameters. I can within a matter of 1 second predict that the new weld width is going to be 375 microns, and then from there you can deduce other information as well. So all in all, these are the three modules that we are going to look at. And yeah, so now is the moment when we want to really show the world what we have developed. So this is the first time we are officially going online, showcasing a live demo of our product. And when we say it's world's first all-inclusive 3D computational modeling software for AM industry, you will really see why that's the case. So I'm going to minimize my screen and move on to the live demo of the software. Okay, so this is my screen as like any other screen. I'll just launch AM Prava from here. First, a terminal will launch, which will dynamically keep showing all the activity that the user is doing in the graphical user interface. So this is the graphical user interface that we were talking about. And on top, we have a navigation bar with three types of modules: computational physics-based macroscale module, Monte Carlo-based microstructure module, and deep learning-based AI module. So let me start a sample project. Let's call it second demo. Okay, I'll just hit create. I'll put it somewhere. Okay, so it says success project is initiated at this particular location. So now you have a project and all the data will be dumped there. So let's start with the macroscale module first. Okay, the module is divided in settings, and then there are some action buttons on the left hand side. So settings, as the name indicates, you start with the material settings first. We have a choice of alloys that we can pick from. You can see your alloys will be automatically updated. If not, you want to create your own alloy, you can just hit create new alloy and provide your own properties. So this is really handy that way. For now, we'll just stick with Ti64. And then we also have similar capabilities for choosing the shielding gas. It could be argon or nitrogen. And then the vaporization is on. And we have realized that vaporization has to be on. We save this, and everything is reflected on the terminal here. Go back, go to the process, and then now this is where you provide all your process parameters. You define what are your laser properties, how do you want to prepare a bed. So laser properties, we first just go upload the scan pattern. So we have provided some sample scan patterns, but you can upload your own. By the way, everything that you will see throughout the presentation is extremely customizable. So let me see. So I just uploaded the scan pattern. I want to show you how the scan pattern really looks like. So where did I save this project? Let me check this one more time. AMP test, second demo. Yeah, here it is. Okay. So this is how the second, the pattern looks like. So in the first column, we have the layer number. The second is the time of the laser. The third one is the XYZ coordinates. So third, fourth, and fifth column are the XYZ coordinates. And the last column indicates that at a given time, whether the laser is on or off. So you can imagine you can give as complex of a scan pattern, and we'll see some complex scan patterns eventually. So that is done. So once the scan pattern is uploaded, we can decide what direction is laser hitting, what is the spot diameter, Fresnel reflections. And let's say for the sake of this demo, we'll make the power 300 watts. Okay. Then moving on to the powder bed preparation. This is again in the hands of the user and completely customizable. So what this button does, it lets the user upload his own powder bed distribution. Okay, and let me show how that looks like. So we are going from a powder radius size of 14 microns to 24 microns with their individual fractions. Okay, and then again, you can provide your own list with your own fraction distribution. Okay. So that's about software. And everything you are doing, it's showing it you in green. If anything goes wrong, it will write the message in red that you know something has gone wrong. And then we have a spreader clearance, spreader velocity, and then something very important, which is the initial chamber conditions. So in this case, my system is already preheated to around 900 degrees Celsius or 1200 Kelvin. You know, I'm currently going to run the demo in atmospheric pressure, and initial substrate height is 0.0002 meters. And then I also provide number of scan layers here because that has to match the number of scan layers you've actually provided in the scan pattern. I hit save, go back, and that's it. I'm done with the process parameters. Then I go to simulation. This is the most neat looking module, but there's a lot of complex algorithm calculations happening in the backend. So you have accuracy, performance, and data saving frequency. You can choose to select a very high accuracy, but your simulation runtime will go high, or you can choose to go with a higher or lower performance, and accordingly your simulation runtime will go high or low. Typically, accuracy and performance are inversely proportional. Data saving frequency indicates how much data you want to save on your computer, or how frequently you want to save data on your computer as the simulation is running. So if you don't have a lot of storage, you don't want to make the frequency very high. So for this demo, we'll keep it at the default frequency. Another very important feature that really binds you, that commercial software bind you with, is how many physical processors you can run this solver. So my computer has 12 physical processors. That's why it is automatically detecting that. The software automatically detects the number of processors on my motherboard, and it's showing 12 are available. So I can choose any number up to 12. There's no license limitation from the number of processors. So I'll just go with 4. I'll save it. Okay, as soon as I save it, it's saying that the mesh size in the backend is 77.5 microns. My core number is set to 0.5, and my maximum time step is 0.75 microseconds. Yeah. Okay. I go back, and just for the sake of safety, hit save all one more time, and just run the solver. There we go. When I run the solver, I see processing and generating mesh, start of layer 1, preparing powder bed using discrete element model. So right now your powder bed distribution is happening, and we'll see all these things in a visual way as well as the simulation proceeds. Let me, I will leave it as it is and move on to the, okay, so it has actually started. So powder bed preparation is done. Now it is actually modeling the melt pool dynamics using multi-phase CFD. And if I hit launch console at this point of time, it is going to show you all the residuals, the actual calculations that are happening behind the scenes, different types of solvers. It is also conveniently telling the user how much storage is already used, how much storage is required, what is the elapsed clock time, how much remaining clock time, what is the, how much percentage of a simulation is completed or not. I can keep refreshing this, and it will show, these parameters will give you a good idea whether your simulation is converging, whether it is running stably or not. So looks like everything is flat, only mild fluctuations. So it's a fairly stable simulation. Okay, so I will let the simulation run. It will take 10 to 15 minutes. In the meanwhile, let's move on to the microstructure module. And again, we have the settings tab here where you upload your scanning pattern. So let me upload my scanning pattern, your melting temperature, thermal diffusivity, thermal conductivity, and all the other process parameters. Now, one thing that is limiting with Monte Carlo algorithms or the simplistic diffusion, thermal conductivity, and diffusion based or sort of solvers is the melt pool is not accurately captured. To that end, what we have done, you will either know the depth and width of your melt pool from experimental data. If not, you will know that from your macro scale simulation. So you see how all these three modules tie into each other. You pick that melt pool depth and width, and then use these correctors to actually create the correct melt pool depth and width, and go from there. And again, in the end, we have some computational settings such as accuracy, performance, data saving frequency, and how many cores we want to parallelize on. So we have already used 2 cores on macroscale. Let's use 2 cores on microstructure. Let's go with an accuracy of 20. Again, this is all to wrap up the demo in a short span of time. Data saving frequency to 25. Okay, hit save. So it's saying that the lattice size is 2.4 microns and it's going to write at a much higher interval now. So not a lot of data is saved. Okay. I save one more time for the sake of it and hit run solver. So it's saying launching microscale modeling with AM PravaH, modeling grain morphology evolution using modified MC POTS model. And this is happening in parallel because we have provided two solvers, or we have provided 2 cores. Okay, so let's see what's happening behind the scenes. So yeah, the simulation is running. It's saying that the estimated required storage is 4.2 gigabytes. The simulation is already 3.8% complete. So I will let this simulation also run in the backend. Let's move on to the AI module. Okay, so what we'll do, we'll upload some NIST experimental data and we'll try to predict the melt pool width. Okay, and I'll show you the whole process of doing that. So let's say the name of the model is Xiang, okay, and then the model complexity is 8. This basically means a number of neurons for those of you who are from that background, number of neurons in the first layer and the consecutive layer. So there are a lot of calculation happens based on this single number. We upload the NIST data set. So this training features, we upload that, and then we upload the melt pool widths. Let me show you how this data looks like. So I just uploaded the training features. So this is what we got from the NIST website. So we have power, welding speed, gas flow rate, focal position, material thickness, weld number, and cross section. So based on this 1, 2, 3, 4, 5, 6, 8 parameters, NIST has also reported how much seam width. So this is a welding data set. How much weld seam width of the copper they were getting in micrometers. You can see based on those 8 parameters, every time the weld width is changing. So what I did, I uploaded the parameters on which weld width will change, and I also uploaded the actual weld width here. Okay, once that is done, I hit train, and then you see on the console it's showing a snippet of the data that I uploaded, and then it's also showing the complexity of the neural network, and it's saying training AI agent Xiang. Okay. So if I launch the console at this moment, wow, we really love this console. You can see that our data is training. We refresh this. So what you are seeing here is that as my model Xiang is training, it's just learning from the NIST dataset. The error is decreasing. So what you have on the y-axis is a representative error, and then I can keep refreshing it, and it will try to learn it better and better. Okay. And then there are more graphs, very detailed data sets that can come out of this, histograms, contributions, whatnot. So those of you who are into that background will connect to it better. Okay, so now that all of our models are running, let me go back to the simulation. Let these simulations run. Let me go back to the next few slides, and we'll come back to the visualization of the results in a bit. Okay, so like the previous speaker said, every parameter matters in additive manufacturing industry. You cannot ignore anything. If you do ignore anything, then you may end up getting very different results, and the entire manufacturing pipeline might be a mess. Okay, so to that end, we'll show you some variations. So let's say if you ignore vaporization versus you do not ignore vaporization, what happens? So the top video, vaporization is on, and in the bottom video, vaporization is off. They are quite similar, but notice when we keep the vaporization on, which is the real case scenario, in reality, vapor might be formed. You are getting a defect, but if you do not keep vaporization on, you will not get defects. We are world's first software who are trying to capture vaporization as a complete volume of fluid system, and therefore we are getting these defects. But there are some commercial software that claim that they can do this defect prediction, but they are fundamentally wrong in saying that simply because vapor has to be treated in a proper phase. Okay. Then let's look at deep versus shallow melt pool. So of course, depending on your properties of your alloy, properties of your process, you might get different types of melt pool depths. Fresnel reflection is very critical. Again, this is something which is typically ignored. If you have very high amount of Fresnel reflection, all your laser will be reflected out at the surface and some of it will penetrate into the surface. If your Fresnel reflection is too low, the vice versa will happen. But what we want to show here, on top we have the right amount of Fresnel reflection based on the material and the laser we are using. And in the bottom one, we have very low Fresnel reflection, which means all the laser is getting absorbed into the system, hence unrealistic defect formation, very deep melt pools, and I mean this is not the reality. Okay, then what is the difference for different laser powers? This is easy to guess. I mean, the higher the laser power, if you see on the bottom of the screen, 400 watts, lot of defects formation, very deep keyholes, those type of things will happen. Velocity of the spreader, even that affects how you're putting powder. If you move your spreader too fast, then you won't have enough particles here. You won't have enough powder. You will get a very bad powder bed prepared. If you move it very slowly, then of course you will get very good powder spreading. A lot of particles will actually be there. And again, with different amount of particles on the bed, you're going to get different melt pools and hence different amount of defects. Okay, should the particle size be big or small? So first of all, this is how we are doing the particle spreading using a spreader. So you see, this is a very high fidelity discrete element modeling that is happening behind the scenes. So remember when I showed the demo, it was saying spreading powder bed using DEM. So this is what it was doing in the backend. Okay. And then if you go with very big particles, which is on the left hand side, and then if you go with very small particles, which is on the right hand side, you're going to get different surface finish, different amount of defects. Scan tracks. This is something that gives us a lot of confidence as a software developer. We start with a very simple scan track, which is single layer going in one direction. Okay. Then we go to a much complex. So this is a small hash spacing, 3 tracks back and forth in a zigzag manner. Then we start going to non-tangential or not non-linear tracks. So we have this circular track going 3 times over each other. Right. And then lastly, we have the more realistic, complex scan pattern. And just notice the surface finish on this track. Really, really high fidelity that way. Moving on to preheating, do you want to preheat your material? You don't want to preheat your material. Again, this will affect a lot on how you get your grain sizes, the mechanical properties of your system. Your grain size can be small or big. Again, that will affect the mechanical properties. Okay, so all this is to say that everything matters, and it is very important that this is critically analyzed using a virtual tool, which is cost effective, which is data safe, and can be deployed easily. Okay. So let's go back to the results, and hopefully everything should have run by now. Go to the terminal. Okay, so it's saying completed. Yes, success. AI training with AM Prava is successfully completed. A microstructure modeling with AM Prava is successfully completed. And let's look at macro scale if that is completed or not. Okay, so that's still running. I will let it run, but I'll show whatever results we have for the other two. So because microstructure is completed, let me show the results here. So I just click on show results, and it's preparing files for visualization. It's going to take a while because we use a very advanced processor, so all the results will be converted to a standard format. Okay, while this happens, let me finish the AI module first. Okay, so now that our model is trained, we want to load that trained model. So remember the name of the module was Xian, and I go to what was the name, second demo. Right, so I go to second demo. Oh, here we go. So in the meanwhile, our microstructure results are also loaded. So a lot of this is happening simultaneously. So I go to the AI saved models, click on Xian, click OK, and our AI model is loaded. And now we are going to predict some the melt pool or the seam width or the weld width for something that we don't know what should be the weld width for that, for a set of parameters. So we'll do predict features, click open and then hit predict. So you can see it is predicting 197.5 microns for one set of parameters, 212 microns for another set, and then all the way to 208 microns as well. So all this data, the module has never seen, but it's still predicting, right? So that's the type of simulation AI module, and you can see when I hit predict, it took only 1 second to give out the melt pool width for 1, 2, 3, 4, 5, 6, 7 set of process parameters and alloy. Okay, so this is what I was doing. Now in the background, my microstructure simulations are already loaded up. So let me reload them one more time. Okay, and I think it might still be running, but I will show you whatever we have right now. Hit apply, show plane. Yeah, so let me play the video. Yeah, so this is done. How the microstructure is evolving. We can see the misorientation angles, Euler angles, temperature distributions and everything. So this is the visualization for microstructure. And let's go back to macro scale one more time and see if that is still done or not. At least look at the console. Okay, so 87% is done, but I will still load up the results because you can load up the results while a simulation is running. So I'll just click on show results. And there we go. We have our results ready here. Let me reduce the fidelity for better visualization. Let me play this video. So, I mean, just imagine this is within 10 minutes of duration. And, I can do very advanced post processing on this. I'll just click on this, take a slice from the center, deactivate the other two clips, and of course all this is included in detail on a manual as well. And if I want to just look at alpha.solid, you can see how the defects have formed. I mean, the amount of porosity is fairly huge. Proper pores are formed, even with such a coarse fidelity simulation, where the accuracy was set to very low. You can see the amount of defects in the system. So this is the type of visualization that we can do using AM Prava. Now all this is fine, but we have also added a help button which will take you directly to our website, and yeah, it will take you directly to our website dedicated to AM Prava and everything that we are committed to. And then there we go, AM Prava user manual. Click on introduction, installation guide, how you get acquainted with GUI, macro scale modeling, how you want to set up the macro scale modeling, different suggestions, recommendations for parameters, how you want to prepare your CSV files, how you set up your scan patterns, spot radius, how to interpret the results. Everything is in great detail. So at this moment, at this time, I just want to thank my team for putting together this very detailed manual. So yeah, really good that way. Okay, so yeah, I mean that's basically it. I can go back to the home terminal, create another project and go from there. So that's on the demonstration front, and a couple of more slides. Just want to show that very soon, we have not stopped developing. There's a long way to go. We have already developed solvers for wire DED process. powder DED process. I think that will excite a lot of people in the group. And we are also working on layer-wise part scale thermomechanical deformations module at this time. Okay. This is our homepage. Our website is www.paandavapplications.com. This is our homepage, and especially dedicated pages for AM Prava software and the manual. So I invite you all to take a sneak peek at the software. We are starting a campaign for discounted licenses for the next 2 weeks. You can just scan this QR code and sign up. It will take 5 seconds of your time. If not, we will also provide the link to that form in the Google in the chat, in the Teams chat. And like the previous speaker said, we are not only targeting accuracy, we are also targeting performance, cost effectiveness, and the dedicated support coming straight from the team of developers and not sales engineers. So that's it from my end.